Welcome to Disc 2 of Irrigation Design Fundamentals. To start this disc off, we're going to go over some keys to designing with drip irrigation. Drip irrigation is the process of slowly watering in gallons per hour, in most cases, compared to gallons per minute. Drip irrigation pipe is normally half-inch diameter flexible tubing. Built into the drip irrigation pipe are emitters. Emitters are mechanical devices that deliver water. So, out of these emitters, the water drips out. You can get them in different gallon per hour emitters. Some of these emitters you can get in half a gallon per hour, 1 gallon per hour, and 2 gallons per hour, depending on the manufacturer. You can also buy them where they're installed with different spacings. The distance between the emitters. You can get them with 12-inch, 18-inch, 24 or 36-inch spacings. For today's example, we're going to say our emitters are installed in half-inch drip tubing with 12-inch spacing between the emitters, and each emitter is going to put out 2 gallons per hour. So each one of these emitters is going to be spaced at 12 inches, and each emitter is going to deliver 2 gallons per hour of water. We're also going to designate the soil type as a clay soil where we're installing the drip irrigation. In general, clay soil has a characteristic where water moves horizontal through the clay compared to sand or sandy loam where the water moves more vertically. So when this drip irrigation is laid out on top of a clay soil, the water is going to spread out on the surface of the clay and slowly drip down through the clay soil. So an example we're going to use today is that we have an area that is 8 feet by 50 feet. And this drawing is not going to be to scale. But we'll say we've got a bed area that's 8 foot by 50 foot, and we want to water it using drip irrigation. And again, what we're going to use is half-inch drip tubing with emitters that are spaced every 12 inches that are delivering out 2 gallons per hour out of each emitter. So to design this with drip irrigation, one of the first steps we'd like to do is to convert feet to inches. So here we have an 8-foot section times 12 inches gives us 96 inches, and we have a 50-foot side times 12 inches gives us 600 inches. So our 8-foot side over here is 96 inches. Our 50-foot side is 600 inches. We'd also, on our second step, like to subtract a 4-inch border. Because when you install drip irrigation, it's a good idea to leave yourself about 4 inches away from any edging, foundation, concrete, or obstruction that might cause damage to the drip irrigation tubing. So what we're going to do is come in here and take off 4 inches off of this side, 4 inches off of this side, 4 inches off of this side, and 4 inches off of this side. So we're actually going to reduce the size of this by 4 inches on all 4 sides. And again, this drawing is not to scale. So we've actually, on this 96-inch side, coming down here, we've taken 4 inches off of this side, 4 off of this side, so we'll subtract 8 inches, which is going to give us an 88-inch side there. And off our 600-inch side, we'll be subtracting 4 inches over here, 4 inches over here, so a total of 8 inches, which will give us 592 inches. So now our new measurements across our 8-foot side is going to be 88 inches, and across our 50-foot side is 592 inches. And again, at any time during this DVD, if you're not picking up these concepts, please stop the DVD, rewind it, and study them again. Now that we have our feet converted to inches and we have our 4-inch border subtracted on all 4 sides, the next step we're going to have is to figure our row spacing. To calculate row spacing, we're going to use our 88-inch side right here to calculate how many rows of tubing we're going to have. So our row spacing formula is going to be to take our 88-inch side and divide it by our target row spacing, which we're going to use 12 inches. We're going to use 12 inches for our target row spacing because our emitters are already pre-installed in the tubing every 12 inches apart. So this is kind of like our head spacing. Every 12 inches we're going to have an emitter. So if our head spacing is 12 inches, we're going to have our target row spacing at 12 inches also. So our row spacing formula will be 88 divided by 12, which gives us 7.3, and we'll round that down to 7. And then we'll take our 7 and divide it back into our 88, which gives us a 12.57 inches row spacing. So once again, we got 88 inches. We divided it by our 12 inches head spacing, which is our target row spacing. We rounded that answer to 7 and divided it back into our 88 inches, which gives us an actual row spacing of 12.57 inches. The next step, after we determine our row spacing, will be to see how many rows of drip we're going to have on this design. If our row spacing is every 12.57 inches, we'll start with our first row of drip right here at 0 and put our first row of drip in. Then we'll come up 12.57 inches and put our second row of drip pipe in. Then we'll come up for every row another 12.57 inches. So our next row will be right here at 25.14. Then we'll come up another 12.57 to put our next row at 37.71. Our next row at 50.28. Our next row at 62.85. Our next row at 75.42. And then complete it with our next row at 87.99. So from starting at 0, we've got 1, 2, 3, 4, 5, 6, 7, 8. A total of 8 rows of drip irrigation along that 88-inch line. Another way to calculate your rows would be to take whatever this number is right here, and it's the same number we divide into the number of rows, and it'll always be one more because we're starting at 0 to complete our total of 88 inches. So it would be 7 plus 1 would equal 8 rows of drip tubing. Now that we've got our 8 rows of drip tubing established, we know that each one of these rows is 592 inches long. Because from right up here, we calculated this entire length was 50 feet. We converted it to inches to get 600 inches, and then we subtracted our 4 inches off each side for our border to get 592 inches. So we have 592 inches of drip tubing per row, and there's 8 rows. So that gives us 4,736 inches of tubing. 4,736 inches of tubing. Now to calculate how many emitters we have, we'll have to divide that number by 12 inches. Because we talked about earlier, in our half-inch drip pipe, we've got these emitters every 12 inches. So if we know we have a total of 4,736 inches of tubing, when we divide that by 12, that's going to tell us that we have 395 emitters. And now for our last step, if we have 395 emitters, and we talked about earlier that each emitter on this design was 2 gallons per hour. So 395 emitters times 2 gallons per hour gives us 790 GPH, which stands for gallons per hour. 395 emitters times 2 gallons per hour is 790 gallons per hour. To convert that into gallons per minute, we'd simply divide by 60 minutes, since there's 60 minutes in an hour. So we take our 790 gallons per hour divided by 60 minutes is going to give us 13.16 gallons per minute. So we'll have 13.16 gallons per minute on our drip irrigation zone. So from here we can go back up to our original design and see that this design will have 13.16 gallons per minute of the drip. As far as piping that zone in, there's a number of different ways to pipe in your drip irrigation. Some designers will set their valve and come out and install their pressure regulator and filter, and then run a line and manifold all the drip lines and feed them that way. It's always important to put on a pressure regulator and filter after your valve whenever installing drip irrigation, along with, depending on the manufacturer of drip tubing, you might put in an air relief valve also on your system, or possibly a flush valve on your system also. Drip technology is advancing with every season, and new devices are coming out. It's best to check with your local drip irrigation manufacturer and see all your options available. Now we're going to move on to precipitation rates. Precipitation rate is measured in inches per hour. And precipitation rate, referring to sprinklers, is the rate that water falls to the ground out of a sprinkler head. One of the common formulas is the precipitation rate equals the gallons per minute of a single head times 96.3 divided by head spacing times row spacing. And again, it's always measured in inches per hour. So this is a key formula for irrigation designers to help them calculate scheduling and run times. And again, precipitation rate is measured in inches per hour. Referring to sprinklers, it's the rate at which water falls to the ground out of a sprinkler head. And one of the formulas to calculate the precipitation rate of a single head is to take the gallons per minute of that single head times 96.3 divided by the head spacing times the row spacing. So we'll do an example of a single head method. Well, say we have a 15-foot full circle head that is spaced at 15 feet head spacing by 15 feet row spacing. It is using 4 gallons a minute. We plug those numbers into our formula. The gallons per minute would be 4 gallons per minute times 96.3. The head spacing times the row spacing would be 15 feet times 15 feet. So again, this would be the single head method for a 15-foot full circle head using 4 gallons a minute with a 15-foot head spacing and a 15-foot row spacing. So our 4 gallons a minute times 96.3 gives us 385.2. And we'll divide that by, on the bottom, 15 times 15, which is 225. So 385.2 divided by 225 gives us a precipitation rate of 1.71 inches per hour. And that would be the single head precipitation rate formula. Another way to calculate precipitation rate is to do it by a zone, by an area, a section, or a valve. This would all be the same thing. We'd be calculating precipitation rate off of a zone, an area, a section, or a valve. The formula for that precipitation rate would be the PR equals the total gallons per minute, which would be the gallons per minute of the zone, the area, the section of the valve, times 96.3 divided by the total area, which would be the length times the width. So the PR would be the total gallons per minute of the entire area times 96.3 divided by the total area, which is the length times the width. And again, it's measured in inches per hour. So an example of that would be if we had a valve in a yard and this was our area, and we had a 15-foot spacing here and a 28-foot line here. And our sprinkler heads were in square spacing. With our valve in the middle, center fed. And we said that these were 15-foot heads with our quarters in the corner being 1 gallon apiece, and our halves on the side being 2 gallons each. And we wanted to do a precipitation rate for this zone or this area, this section or this valve. We'd use our formula up on top. So we take our total gallons per minute, which here we've got 1, a 2, and a 1, a 1, a 2, and a 1. So we have a total of 8 gallons per minute times our 96.3. So our formula would read PR equals 8 times 96.3 divided by our total area. Our total area is the length times the width. So we have a 28-foot side and we have a 15-foot side. So that would be our formula written out. 8 times 96.3, which gives us 772.8 divided by 28 times 15, which gives us 420. So 772.8 divided by 420 would give us a precipitation rate of 1.84 inches per hour. So those are two of our ways to get precipitation rate. One is by a single head, and the other is by a valve, section, area, or zone. So what this zone is telling you is that if it ran for 1 hour, it would put down 1.84 inches of water. That would not be good scheduling because you would have a lot of runoff on that zone. One way to determine how long that zone should water to put down 1 inch of water would be to take your 60 minutes an hour and divide it by your precipitation rate. So in this example, we'd have our 60 minutes an hour. We divide it by our 1.84 inches per hour precipitation rate, and that would come up with approximately 32 minutes to put down 1 inch of water. And I've rounded that number just to make it a whole number. From there, you can determine your scheduling based on your soil type, your infiltration rate, your water restrictions, whether you're watering cool or warm sod, and the time of the year and other factors. One of the keys to precipitation rate is you always want your precipitation rate to be less than your infiltration rate. The soil can only accept so much water, and by keeping your precipitation rate below your infiltration rate of your soil and good scheduling, you can ensure there will not be any wasted water due to runoff. Another way to gather precipitation rate information is to use granulated cylinders called catch cans. Sometimes this can be part of a water audit. A catch can looks something like this. It's a granulated cylinder, and you'll place it in the sod. And this catch can, as the sprinklers pop up and turn on, water will go into the catch can and fill up this catch can with water. The can will have precipitation rates in inches to gather the information, which you can calculate your precipitation rate from. Enclosed in your packet is a catch can diagram similar to the one above. Please open to that page. On that page, you'll see a diagram similar to the one in front of you. Inside the circles are letters A through G, and below that there are precipitation rates gathered in the catch cans. For example, A is showing to have 0.33, B 0.43, and so on. The question on the bottom says, what is the precipitation rate of this area if these totals are for a 15-minute cycle? It's important to remember that precipitation rate is measured in inches per hour. So if this was a 15-minute cycle, we'd have to convert that into 1 hour of precipitation. So let's get started. Here is can A, and here is can A. There's two can A's. It says they are 0.33 each. Here's can B right here. So there are two can B's, and can B says it is precipitation rate's 0.43. Here's can C right here and here, and again there's two can C's, and catch can C says it's caught 0.22. And then we come to catch can D, and the corner up here and the corner down here, so there's two of D. It's showing D has caught 0.19 of precipitation. And then across the middle, we've got can E here, can F here, and can G here. And those are corresponding with E has a 0.33, F has a 0.55, and G has a 0.42. When we add up all this precipitation, again counting these first four cans twice since there's two each of those, we get a 3.64 precipitation reading. But once again, the question says that these readings were taken for a 15-minute cycle. Well, to get precipitation rate, we need 1 hour. It's measured in inches per hour. So we'll have to multiply this number times 4 to get 60 minutes of precipitation. Because this number is only for 15 minutes, we'll need to get 60 minutes, so we'll need 4 15-minute cycles to make 60 minutes. So on our calculator, we could do 3.64 times 4, which is going to give us a 14.56. Precipitation rate for all of the cans. Now we need to add up how many cans we have. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So to get an average precipitation rate for all these cans, we'll have to take our 14.56 and divide it by our total number of cans, which is 11, which will give us a 1.32 precipitation rate in inches per hour. So those are three ways to calculate precipitation: by an individual head, by a zone or a section, using the formula, or you can also perform a catch can water audit. Once you've calculated your precipitation rate in inches per hour, another formula you can use to determine how many minutes you should water would be to take your soil infiltration rate divided by your precipitation rate times 60 minutes. To get your soil infiltration rate, you could do a soil sample and send it off for testing. There are also charts available that show average infiltration rates on soils based on their content and compactability, and some general infiltration charts on different types of soil like sand, sandy loam, and clay. For this example, we'll just say our soil infiltration rate is 0.45 inches per hour. In the calculation we just did, our precipitation rate is 1.32 inches per hour times our 60 minutes. So we'll do our 0.45 infiltration rate divided by our 1.32 precipitation rate, gives us a 0.34 times our 60 minutes. Which gives us approximately 20 minutes. So solely based on the infiltration rate versus the precipitation rate, what that's telling us is that that zone could water for approximately 20 minutes before the soil would be full and possibly have runoff. Other factors would also have to come into consideration, like slope, whether it is a flower bed or turf area, and a few other factors. One more precipitation rate calculation we're going to do would be in more of a word question. And we'll say we'd like to find out what is the precipitation rate of 4 4 gallon per minute rotors. Spaced at 30 feet by 30 feet. So this question would read, what is the precipitation rate of 4 gallon per minute rotors if their spacing was 30 feet by 30 feet? Well, first we want to write out our precipitation rate formula, which would be our, for an area, it would be our total gallons per minute times 96.3 divided by our length times our width, measured in inches per hour. So if we were to draw this out, it says we've got a rotor, a rotor, a rotor, and a rotor. And these rotors are spaced 30 feet, 30 foot, 30 foot, and 30 feet. And it's saying that each rotor is putting out 4 gallons per minute. So, going back to our formula, our total area, our length times our width, would be 30 times 30. Looking back at our drawing now, these 4 rotors are full circle rotors. So if these are full circle rotors, that would mean this rotor right here is throwing water into this area, but it's also throwing water outside of this area. So the total pattern is going to look something like this. If this is a 4 gallon rotor, 4 gallons per minute, the water it's throwing into this area is not 4 gallons. It's just 1/4 of 4, or 25% of that water is coming into here, because the rest is going outside that area. So that means of these 4 gallons, 1 gallon is coming into this 30 by 30 area. The other 3 gallons are going out in this other area. So we will not include all 4 gallons when we calculate our precipitation rate for inside this 30 by 30 area. We'll just include 1 gallon from this rotor. This rotor will be the same way. It's a full circle, so this 1 gallon from it is coming in this area. This is a full circle, so there's 1 gallon from it. And this is a full circle, so there's 1 gallon from it. So within this area, since these rotors are full circles, there's just going to be a total of 1, 2, 3, 4 gallons. Now if those rotors were quarter circles, where all the water from those rotors are going into that 30 by 30 area, then you'd use the total gallon per minute, and it'd be 16 gallons a minute, because you'd add all 4 from each rotor into it. But because we designated their full circles, we just have to use 25% of the gallons that are going into that area. So back to our formula. Our total gallon per minute would be 4 gallons per minute. So when we do our calculations, we'll have on the top, we'll have 96.3 times 4, which gives us 385.2. On the bottom, we'll have 30 times 30, which is 900. So we've got 385.2 divided by 900, which gives us a 0.428 precipitation rate in inches per hour. So you can see how rotors put down water at a much slower precipitation rate in general than spray heads. So in areas where you have a lot of slope or where you are concerned about runoff and it lends themselves to rotors, rotors will put down the water at a slower precipitation rate and could help reduce runoff conditions.